Good morning to everyone. Okay, let's do this problem. I've kind of worked out how I want to describe it, so we should be good here. We are looking at an AP Physics C, E, and M problem from 2008, question number 2. In it, we have this circuit, as seen here, consists of an EMF of 1500 volts, a little switch in the beginning, a resistor of 200 ohms, and then a parallel branch with one side having a resistor of 300 ohms, that's R2, and the other branch having a resistor R3 of 100 ohms and some jump patch A to B, which we're going to put a bunch of stuff into it. We're going to pop into that patch AB a resistor, an inductor, and a capacitor, and look at the potential difference across different components of our circuit here. Now, an important thing, kind of before we begin this, is to remember a few things. We know we're going to have capacitors and inductors on this test. So let's talk about a capacitor real quick. A capacitor at time equals 0 for an uncharged capacitor. If you're charging up the capacitor, it's uncharged at time equals 0. It is going to act like a short in the circuit. All of the current is going to run through it. It's going to act like it's not even there. It's going to act as just a wire. Okay, so it's going to act as just a wire. At time of infinity, your capacitor has been completely charged. And when your cap has been completely charged, what we're going to see is it's going to act as a break in the circuit. It's going to shut things down right there. For an inductor, if this is a uncharged conductor or a conductor that doesn't have a steady state current flowing through it, there's our inductor. At time equals 0, we're going to think of our inductor kind of as a break in the system. It's just actually the flip of the capacitor here. So, initially that inductor is not going to have anything flowing through it. It's a break in the system. At time equals infinity, a very long time later, we're at a steady state in the system. And when that happens, the current is no longer changing. And this is all for DC currents, by the way. The current's no longer changing in that inductor. So it's just going to act as a short, or what we can just think of as a wire. So the capacitor and the inductor can just thought of kind of backwards. A lot of people have problems thinking about inductors. They're kind of tricky to think about because you're thinking about the changing of the current in order to cause their effects. The cap is pretty easy to think about. You're just thinking about it charging or discharging. So if you'd like to memorize the capacitor and just flip it for the inductor, that's what I recommend to do. But understanding what's going on there as well is important. What we're doing in the circuit here, though, is as we're going to hook pieces up across A and B, we're looking for the potential difference, so the voltage drop across R2. So we want the voltage drop from, well, we could think about it across the resistor, but we could really think about it from here to here, because that is the voltage drop just across that resistor with ideal wires. So how are we going to go about doing this? Well, first what we're going to do is in part A, we are going to hook up across A and B a 50 ohm resistor, and then we're going to try to figure out what that voltage drop is. So if we want to find a voltage drop, remember, we are left to use Ohm's law, and Ohm's law is V equals IR. And we know what that resistance is across R2. It is the 200 or the 300 ohms, excuse me, we had just up in the diagram. What we need to do is we need to find either the current running through that circuit branch, or if we could figure out how much voltage is being taken away initially by R1, then this drop here to here from the yellow to the yellow will have to be whatever's left over, because when we come back to our EMF, we've got to be back at 0. So if, let's say, R1 was taking like 500 volts, then R2 would take the rest of it 1,000, because 1,000 and 500 add up to the 1,500. So we could do that in either way. We could either find the current running through R2, or we could just figure out what R1 is taking away there. And either way, we'll find our answer. One of the things we have to do before, though, is we need to find what the total current is in the system. And the only way to do that is to find an equivalent resistance and use Ohm's law for the entire system itself. To find an equivalent resistance of the system, or a total resistance of the system, we have to add everything up here. Now, the 300 ohm and then the 150 ohm, we have to do a little bit of resistor addition in order to find that. We should remember that resistors R3 and this 50 ohm resistor here, these are in series, and whenever you have resistors in series, you just add them up. So this 150 are going to be together as a 150 ohm resistor. However, when we go to add up, when we look in this parallel branch here, the 300 and the 150 total, we have to add up those resistors in parallel. And we can get the in parallel equivalent resistance here as saying it is 1 over the equivalent resistance equals 1 over 300, the first resistor, plus the 150 total here, because we've added those up in series. So 1 over the quantity of 1 over 300 plus 1 over 150 equals 1 over the equivalent resistance. So make sure you take the reciprocal of that in the end. If we do this, let's see what that gives us. 1 divided by 300 plus the quantity of 1 divided by 150, 1 divided by that. We see that this equivalent resistance here gives us 100 ohms. So our total equivalent resistance is going to be the 100 ohms from everything going on over here, plus, because now we're in series, the 200 ohms from before, which gives us an equivalent resistance of 300 ohms. To find the total current in our system then, we can take Ohm's law, V equals IR. So the 1500 volts of our EMF is going to equal to the total current times the total resistance of 300 ohms. That gives us a total current of 5 amps, just dividing 1500 by 300. If we know the total current here is 5 amps, well, this current is running 5 amps through this resistor, but at this point it's going to break into 2 different current components here, which will add back up to the 5. I don't really want to figure out what the 2 current components are. It's actually going to be easier for us just to do 5 times 200. That equals 1000 volts. That's how much voltage is dropping across R1. And like we said before, if we figured out what's across R1, then what's ever going across the R2 branch or the R3 and the 50 ohms will be the same, and that's just whatever's left over. So 1500 minus 1000 gives us 500 volts left over. So we can just say that the voltage across R2 is equal to the 1500 minus the 1000 from R1, which is 500 ohms. If we wanted to figure out the current going across that, we could have. We didn't have to. I prefer not to. I think it's easier doing it this way. We could have also done a Kirchhoff loop to figure out the current across R2 and then just multiply those together if you're big into Kirchhoff's loops. But we didn't have to. So a lot of different ways to do that one. And a lot of stuff that we just wrote up here on this. So let's clear that out a little bit. And we're actually going to take a look at part 3 next, looking at a capacitor, because capacitors are a little bit easier to think about. So in part 3, we are putting an initially uncharged capacitor right here across A and B. And we're once again asked, what is the voltage drop across the R2 branch? So what is the voltage drop here to here? Well, what we need to remember for the R3 branch is that capacitor being uncharged, it is going to act as a short on the system. So it is really, we can just think of it as a wire. If that cap wasn't even there and it was just a wire, like, same thing would occur. So if we think of it as just a wire, then we have the same problem as part 1, except there's not an extra 50 ohms here. We don't have to worry about setting up that little series branch before the parallel branch. So what we can do this time is we can just say that for our parallel branch here, 1 over the equivalent resistance equals 1 over 100 plus 1 over 300, and that is 1 over that quantity. So what we find for the equivalent resistance across that little branch there is, let's see, 1 over 300 plus the quantity of 1 over 100. The inverse of that, so I get 75. And then I need to add that to what happened in the beginning here in series, the 200 branch. So plus 200 to 75 will give us 275. If that's the equivalent resistance of the entire circuit, then by Ohm's law, 1500 volts equals the total current times this 275 ohms, which gives us that our total current is 5.54. So that's 5.54. Oops, put a 4.5. Oh no, it is 4.5. Haha. 5.45 numbers, amps. And if I know what that total current is coming out of the EMF source at 5.45, I can do just what I did in part 1. I'll figure out the voltage running across this, and I'll just subtract it from the 1500. So 5.45 times 200 ohms gives us 1090 volts across here. And what we can say is, knowing that 1500 minus the 1090 is going to equal the voltage across R2, which means the voltage across R2 is going to equal 409, or about 410. Let's just put in a 410 ohms here, or 410 volts, excuse me. That's just because we found out what happened on the first one, so the rest of the circuit has to take that amount. Okay? So that's what we did with the cap. Now, on the flip side of things, when we look at the inductor is not going to act as a short circuit immediately. The inductor, immediately when we start, is going to act as a break in the system. If we recall, it's just the opposite of the capacitor. So if we think about the inductor initially, we're still looking at the potential from across R2, but now we've got a little inductor here. Now if we're looking at the inductor, since this essentially acts as a break, we are not going to get any current running through this branch. So this branch doesn't even really exist for us in this scenario. The only thing we have in this scenario is a current wrapping in here, which means when we go to do this, we can just say that the equivalent resistance of our circuit is the 200 plus 300 ohms, which is 500 ohms. And based off of Ohm's law, V equals R, or V over R equals I, we can say that the 1500 volts divided by the 500 ohms of resistance equals a current of 3 amps. That current of 3 amps is the current of 3 amps everywhere. It's running through the 2 ohm and the 200 ohm and the 300 ohm resistor. So instead of having to do that subtraction part, I can just say that the voltage across R2 is equal to the current running through it, 3 amps, times the resistance of R2, which is 300 ohms, which gives us 900 volts running across R2. Okay, so that's how we can do part A here and all 3 parts of that. It is just a lot of Ohm's law, it's just a lot of looking at that, but it's very important to understand this right here, that at the very beginning of time, a uncharged capacitor acts as just a wire, so you can just think of all the current dumping through it. It doesn't really exist. And for an inductor at the beginning of time, you can think of it as a break in the circuit. It's fully opposing everything. It's a break in the circuit. You can just ignore that entire branch that it exists in. Okay. In part B here, and this is the last part of the problem, we're asked to draw some graphs here. We have the switch is closed for all 3 of the scenarios from before, and in all 3 of these scenarios, we're asked to draw the current in the R3 graph. So we're looking for the far right branch here for all of the cases. Label the graphs R for the resistor, L for the inductor, and C for the capacitor. So How do we want to do this? Well, there are a few shapes that we're going to need to be aware of. If this is, and let's just draw this a little bit better, this is current and this is time. There are some shapes we need to be aware of. Because we've got a DC graph, when everything is just a resistor, as in the 50 ohm resistor we're adding, then I know that my current will remain a constant value. That's Ohm's law. It's just V equals IR. So my current should be some constant line for a resistor graph. Where that line is, we're going to have to check. But for my other two graphs, the inductor and the capacitor, we're going to have some different things here. In this case, for a inductor, that's a poorly drawn inductor. For an inductor, slightly better. There's two shapes I can have, and these are actually the same shapes that I could have for a capacitor. But for an inductor, traditionally, if the inductor is uncharged or doesn't have a steady state current going through it, then as we apply a current to it, we're going to get this shape. And this shape is given to us by that the current as a function of time equals the I naught, the default current, times 1 minus e to the minus, and this is R over L, the time constant for an RL circuit, times the amount of time. So whenever time equals 0 here, t is going to equal 0. E to the 0th power is going to equal 1, and since that's a negative, it's actually 1 over 1, but 1 minus 1 is 0. So that is why this at time equals 0 starts at 0. If for some reason we had a steady state and we opened the switch, what the inductor would do, it would go the opposite direction. It would come down like this, which would be I naught e to the minus R over L times t. Okay, we don't see this. This is already if you had a steady state. No reason it couldn't happen. We just don't see it often on the test. For the capacitor, a cap will take the exact same shapes as the inductor does. For a capacitor, we normally see shapes that are either like this. This is for a charging capacitor, and it takes the same equational form, but we just look at the charge on the cap. Q naught times 1 minus E minus T over RC, where that's the time constant. Or if you have a discharging capacitor, you could have a cap that is doing something like this. So you would have Q equals Q naught E to the minus T over RC. So depending on what we have here, this is a discharging. We're going to have a certain thing going on in this circuit here. So let's look what we have. Well, we know we've got just the resistor here, so let's just draw a flat line somewhere on this graph here. Okay, so boom. This is our resistor graph. Now let's see what we've got for the inductor and the capacitor. It's an initially uncharged capacitor. So if we have an initially uncharged capacitor, then initially all the current is going through it. Now, this would be a charging capacitor here, but this equation here, which goes up like this, that is looking at the charge. It is not looking at the current going through that cap. If we think about just the current, we know we're still going to have these shapes, but the current equations are actually flipped for these here. When we think about that cap charging, it initially is taking a ton of current through the system. It's taking all of it. It's just a wire. And because we've actually, we have a different amount of resistance in this system, we have a different amount of current too. Remember, in part A1, we found that our current was 5 amps. But in part A3, we found our current is 5.45. So for our cap, it's initially taking all of the current here. And it's actually a higher value than what we have for just the resistor setup. And we're going to peel like this. Oops, it's got to get lower down. Kind of tricky graph to draw. There we go, that's better. And it's got to peel down to a 0 at some point, or at least close to 0. We'll never actually reach it. Because as that cap keeps charging and charging, it gets harder and harder to charge. There's more of a pushback there. So this is our capacitor right here. For our inductor, we know our inductor has this equation. We don't have to think about anything weird with the capacitor where we're switching into a current. We have this equation as a current, if you remember it. And we know that because it starts as a break in the beginning, but ends as a wire, then what this means is that in the very beginning, as a broken wire, our inductor is getting nothing, but at some point later on, it is acting as just a wire. And if it's acting as just a wire, then the voltage across that setup there, or rather the current across that setup, could be found with Ohm's law. The current across that inductor later on is just going to equal the voltage over some resistance. And if we take a look at what we have in this problem, because we're looking at R3 in this case, then we know that at some point later, when we get to that steady state, we are going to find a current equal to the voltage across and then that 100 ohms resistance. So what we'll be able to state here is that this graph will arc up and it will actually wind up here for our inductor. Let's put an arrow on this resistor just for proper formalities. Okay. The big thing here is that this inductor graph is arcing in this direction, that concave down look to it. Okay. And 3 graphs, all in the correct form. We've made sure that our capacitor starts a little higher because it had more current. And I think that's good. I think that's a good looking graph right there for what we've got. Took a little bit of thought to get through it. Definitely wasn't easy. Had to kind of remember a lot of stuff to do it, but a lot of points just for graphing. So with that, this problem is finished. Big things to remember were up here regarding this about inductors and capacitors, but those are just things that we have to know as physicists. Take it easy. Have a good one. Go check out another video.